I'm going to be doing homework 4, part D. So this is number 1. We're going to generate synthetic data for the response process of GP is equal to 1.5 divided by 7s plus 1 to the third times 12s plus 1 squared to a step change input of magnitude of 1.2 over 50 times steps for 2.5 time units. We're going to add a Gaussian normal distribution noise for a standard deviation of 0.5 for a calculated response. Okay, so over here, I have this imported our library from GitHub. So the first thing that we want to do is we'll import our GP, and I'm going to use this equation that we have right over here. So it's 1.5 divided by 7 times s plus 1, and then this is to the third power, times 12 times s plus 1 to the second power. And then we're going to put that in there, and I'm going to double check to see if this is correct. Okay, great. So the next thing that we want to do after this, so we have this here. Okay, so the next one I want to do is, so now we can do our simulation, so t and y, and so sim, so we're doing GP, so our actual process, and then we're going to do lambda, our timescale t. So we are given that the magnitude is over 1.2, the time steps is going to be 50, and then our time units is 2.5, right? This is dt. Yep. And so this is our clean data here. So what we want to do is we want to make, like I said, we wanted to make a synthetic data for this. So we're going to do random. So we're going to do y underscore data is equal to np.random. And it said that we are going to use a normal distribution, the Gaussian distribution. So we're going to put normal. And we're going to put our y in here. And we want our standard deviation to be 0.05 for that. So next, we're going to do our figure. So fig.make underscore subplot. And then we're going to do fig dot add scatter. And so x is equal to y. X is equal to t, sorry. Y is going to be equal to y data. And then the mode is going to be markers, just because this is a representation of data, not actual data. Let me update this. Update layout. And I want to do this. It's going to be 800. Right. Okay. Okay, so you can see that this is kind of like following what we're trying to show. So it's kind of around there, right? It's not far from the standard deviation, so it comes up and down. So we did that for our synthetic data, so we can go on to part 2 of this. So we're going to fit a Hw4D model to the synthetic data in part 1 by minimizing the sum squared error between the model and the data. This is going to be a nonlinear regression. So since we are going to minimize the sum squared error, we need to add from scipy dot optimize. We're going to import minimize. Okay, so we did that. So I'm going to put before this, we're going to define our function. We're going to define the Hw4D, right? And this is so it's t, k, it's tau, and then it's theta. Okay, and we're going to return np.where. So our t is going to be greater than theta, and then we're going to have k times our np dot x negative, and then t negative times t times our theta. Now I want to divide this by tau, and divide by tau, and then this is to 0. Okay. And so then after this, we're going to add, we need to do our sum squared error, right? We want to minimize that sum squared error, so let's define our sum squared error. So I have a vector in here. So our vector is going to be, let's unpack our vector. So it's Ka, tau, and our theta. This is our vector here. So after that, we want to do is also, this is 1 minus here. So that's to fix that here. And then for our sum squared error, we want to return. So we're going to return np.sum. So this is for our sum squared error, right? So we're going to subtract our y data, so our synthetic data, minus our functions, the Hw4D, where it's t, k, tau, and theta. Okay. And we're going to square that. Might be Ka actually. Okay, so the next thing we're going to do is our v0. So it's v0 equal to np.array, and it's going to be 1.8, 30, 15. And then we're going to minimize, so we're going to do Ka, tau, theta. And we're going to minimize this, and our sum squared error, right? Our v0, and dot x. And I'm going to loop this here. So we're just going to add another scatter plot here onto this graph. So this is not going to be y data, it's actually going to be our Hw4D with our t, our Ka, our tau, and our theta. And this is actually our data, so this is going to be lines instead, markers. The problem was up here. This needed to be a subtraction. I had it as a multiplication up here. So that does not work. But yeah. So here is our fixed plot. So you can see that our Hw4D follows this line pretty closely without some squared error. So this is a good fit for this line for our experimental data. So that's the end of part 2 for this. We're doing part 3 now. So using the fitted parameters from part 2 and the calculated PI controller parameters by the Smith and Corpio, we're going to simulate a closed loop response to the system to a step change in the step point. So we have all of these. I'm going to use the parameters given, and I'm going to use it. I'm going to get them from my iPad here. So we have first is PA is equal to 0.586. PB is equal to negative 0.5. Then we have IA is equal to 1.03. IB is equal to negative 0.165. And then in our previous problem, we were using Ka, right? We're going to use K this time, so K is equal to Ka divided by 1.2, and then we have our Y, so Y is going to be equal to PA times theta divided by our tau, and then 2 PB. And then another equation we were given was Kc is equal to Y divided by K. And then lastly, we have our tau I, which is equal to tau divided by our IA plus IB times our theta divided by our tau. Okay, that is it for this. So the next thing that we want to do is we want to have our GC1. So our GC is going to be equal to our KC times 1 plus 1 divided by our S times our tau I. And then our GC1 is going to be equal to our GC times our GP divided by 1 plus GC times our GP. Okay, now that we have that, we can do our simulation. So XY is going to be, this is going to be servo equal to our simulation. So we're doing GC1, and then we have our lambda. T is 1, and then N is equal to 1,000, and our dt is going to be equal to 0.1. Okay. And now we can do our fig. 1 is equal to make underscore subplots. And then we're going to do fig 1 dot add underscore scatter. Y is equal to t. Our y is equal to y servo. And then our node is going to be equal to lines. And then we are just going to do fig 1 dot update layout. Width is going to equal 800, height 600. Okay, let's see. Okay, so this is a little different. than what I had. So change that to a 5. See what this does. Okay, so we just changed our step here. So this is kind of similar to what we had in the first place, where we're going down and then we're going back up to correct for it, and then coming down and then having a steady state, having the correct height that we want. So this is the end of homework 4.